Good afternoon / morning, everybody. Welcome to another TACO sponsored webinar. My name is Brett Zerba. I'm an applications engineer with TACO. I will be moderating today's webinar. My coworker, Rich Medeiros, will be doing most of the presentation. Before we get into too much here, we always like to check to make sure folks can see and hear Rich's screen. So if you can raise your hand, so I can see a couple folks raising their hand. Good, George raised his hand. John, Javier, okay, thank you, good. It sounds like everybody is all set in that regard. Thank you very much for doing that. TACO, Thermal Appliance Company, that's what it used to be known as way back 100 years ago when we started. We are a 100-year-old U.S. manufacturing firm headquartered is in Cranston, Rhode Island. Good old Rhode Island. We are owned by the White family, Johnny White, third generation White ownership, is currently the owner and president and owner and everything. Chief bottle washer too. Don't tell him I said that though, please, 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 please. So today's presentation is the first in a series of 6. Usually, and I think I recognize some names here, have been to our facility during the year for a TACO university class. Well, this is kind of an offshoot of that because all of our 2020 classes at the facility, at the factory, have been canceled. So look for them next year. Make sure your TACO reps get in touch with you to come visit us next year. But this year, those have all been canceled. So we will be, instead, we're going to be having them online. So we are having 6 of these classes this Wednesday and every Wednesday following. We offer them at noon and at 3 o'clock. So the same class is offered again at 3 o'clock. I wouldn't participate in both of them unless you'd like to, but you don't need to, that's for sure. A couple of other housekeeping items. Anyone that wants a PDH or attendance certificate, that will be automatically emailed to you for you to download after about 24 hours after the class ends. So we'll get an email tomorrow. Be on the alert for it. It's from the TACO webinar site, and it'll allow you to download it from that email. Also, we are taping this, so a link to that will be sent of the video of this webinar as well. And in addition to that, the webinar video will be available on the TACO website in a few days as well after the class ends. So I think, Rich, I got everything out of the way. Questions. There is a question area. I'll be monitoring questions throughout. Some I may answer directly right to you, or others will bring up for the whole group to answer. Hopefully we'll get through them all, although it depends on how many there are. If we do not, we will directly email you the answer to your question after the fact, the next few days. So keep that in mind. I think that's pretty much it. Brett Zerba, that's my name. Rich Medeiros is going to be speaking very shortly. And Rich, take it away.
Well, thank you, Brett, for that great introduction, and welcome everyone to our fundamentals of hydronic piping systems. And this is known as the manual pressure drop or pressure loss calculation. The reason we decided to put on this session is that a lot of folks are asking, well, where does all that automated pressure drop calculation or software, where does it get its origin? So before I actually get into the software, the presentation, let me just give you a quick introduction to myself. Again, I'm Rich Medeiros. I am a mechanical engineer. My title at TACO is Senior Systems Engineer. I came out of the consulting side of the industry. I am a PE, and I've been doing this for several years. And so I've been, like some of you in the audience, not necessarily all of you, but I worked on the consulting side of the industry. And I specialize in the engineering and design of HVAC systems. So enough about myself. Let's get right into today's presentation. So the things that we are going to be covering today include design criteria, water velocity pressure, pipe pressure loss, fitting pressure loss, valve pressure loss, valve CV, and then questions at the end. So the very first thing when we talk about doing pressure drop calculations is we have to establish the design criteria. And most engineering offices that are involved with calculations, whether they do them manually or automated through software, most people are doing it automated through software today, they do establish some office criteria. And generally the minimum criteria that we see that's established out there is to have a maximum flow. In this case, for today's presentation, it's going to be 8 feet per second. We're going to have a maximum pressure drop of approximately 4 feet per 100 feet. We're also going to have to decide what the fluid is. And for today's presentation, it's going to be clear water. And clear water is defined by the Hydraulic Institute. So it's not potable water. You don't want to drink this water, but it doesn't have any chemicals. It doesn't have glycol. It's not a brine solution. It's basically just clear water. And we also have to establish our temperature and specific gravity. So in this case, the specific gravity is approximately equal to 1, probably a little bit less than that, because we do have a maximum fluid temperature for today's discussion of 180 degrees. So those are the few things that you need to establish when you're talking about doing pipe pressure drop calculations. All right, so now let's get into the very first thing is water velocity. How do you calculate water velocity? And why is it important? Well, remember, we just said that our velocity maximum for our design criteria is going to be 8 feet per second. So using this little example here, I'm just going to do a quick sample calculation to show you how you could manually calculate the velocity. So if you have 6-inch Schedule 40 steel pipe at a flow of 500 gallons per minute, I've got a picture of a steel pipe over here on the right side. Hopefully my pen works. There's my pipe right there. Ta-da! And this is a cross section of that Schedule 40 pipe. Schedule 40, sometimes referred to as standard strength pipe, has an inside diameter of 6.065 inches. Now, again, this is Schedule 40 pipe. If you're using a stronger pipe, say, for example, a Schedule 80 pipe, the outside diameter is still the same. So a nominal 6-inch Schedule 40 pipe has an outside diameter of 6.625 inches. If it was a Schedule 80 pipe, it would have the same outside diameter. However, the wall thickness would change. Wall thickness would increase, and therefore the inside diameter would decrease, and that would affect your velocity at a given flow of 500 gallons per minute. So that's an important concept to keep in mind. Okay, knowing that, let's keep moving along here. Let's calculate the pipe internal area in square feet. And the reason we want to do that is because when we talk about flow for a hydronic system, for HVAC systems, we generally talk about flow in gallons per minute. But ultimately, when we're calculating velocity, we have to know what the flow is in cubic feet per second, assuming we're using imperial units. So in order to make that formula work, the first thing we have to calculate is the pipe internal area in square feet. And the internal area is simply the basic equation of pi d squared. And again, we're using the inside diameter. And so in this case, the internal area is pi d squared, which is, in this case, divided by 4, divided by 144, which converts from square inches to square feet. So it's pi d squared divided by 4 divided by 144. I apologize for confusion there. The pipe internal area in this calculation, by simply plugging the numbers in, comes out to 0.2006 square feet. So now we have the internal area of the pipe. Okay, so the velocity is the flow in gallons per minute divided by the internal area. And we have this constant of 449.4, and that allows us to convert from gallons per minute into cubic feet per second. So when we plug in the gallons per minute, we come up with a velocity of 5.55 feet per second. And in this particular case, since our design criteria was a maximum of 8 feet per second, so this would be an appropriate pipe size for our design. So before I go any further, I know this is going through this quickly, but it's fundamental information. Any questions out there, Brett? Anybody have any questions?
Nothing typed in the question area, Rich, but I guess my question slash comment, the IDs for different types of pipes are available online, right? I think I looked that up. So if it's a copper pipe or a plastic pipe, CPVC, PVC, blah, 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 all that's
Yeah,
available in different locations, right? Or some
excellent
charts.
point. Yes. Today, there's so much information readily available. Back when I started, there was no such thing as the internet, and so you typically had engineering books that had all of this data. And I will show you a page from one of those engineering books in a few minutes.
Oh, good.
Okay.
Thank you.
All right. So
Actually, there's another question. The oh God, 449 factor. Where'd that come from?
well, actually, it just popped up. I clicked on it. If you notice, I put 449.4. And I put an asterisk, and at the bottom of the screen here, 449.4 is equal to 7.49 gallons per cubic foot. That's just a conversion from cubic feet to gallons or gallons to cubic feet, times 60 seconds per minute is equal to 449.4. So if you multiply 7.49 times 60, 7.49 times 60 comes out to 449.4. And that allows you to make the conversion between gallons per minute to cubic feet per second.
Is it pi r squared or pi d squared?
Well, it's pi d squared divided by 4. If you notice in this equation up here, let me get my pen again. So if you were using, it's this equation right here, pi d squared divided by 4, but since we're converting from square inches to square feet, then we want to make sure we divide by 144 to make that conversion.
10-4.
Okay. All right. Continuing along here, I'll erase all that and go on to the next slide. So here is a table that I copied from the internet. And if you'll notice, it has velocity information in it. So we said our pipe was a 6-inch Schedule 40 pipe. So let me get my pen. So here's a 6-inch. This table is set up for new steel pipe Schedule 40, which is standard strength. And if you notice the velocity over here, that's this column, velocity in feet per second at 500 gallons per minute. I go down here to 500 gallons per minute, and the velocity, just as we calculated, is 5.55 feet per second. So I did the manual calculation to show you how you can do the calculation, but most of us today are either using tables like this or we're using an app on our phone. But again, the purpose of today's discussion is to show you where all this information comes from. If you can do it manually, then you can do it using any kind of software or app that's out there. All right, so moving right along, let's erase some of these lines here and go to the next slide and talk about velocity pressure. So again, we're starting off with a 6-inch Schedule 40 steel pipe at 500 gallons per minute. All the other data rather is the same, only this time we're looking for the velocity pressure or head in feet, all right? And the velocity pressure is equal to this equation right here, where it says it's equal to the velocity in feet per second squared divided by 2 times the gravitational constant. And the gravitational constant is 32.2, so 32.2 times 2 is equal to 64. Let me make sure I get my pen out here. Sorry about that. 2 times the gravitational constant is 32.2 feet per second squared, times 2 is 64.4. So if I take my velocity If you remember, we just calculated the velocity a moment ago as 5.55 squared divided by 64.4. And that comes out to, whoops, let me erase that. Sorry about the little tool. I need to erase that. There we go. It's one of the challenges of using these little pens, on-screen pens. Okay, and it comes out to 0.479 feet. And I have an asterisk right after the G, so the gravitational constant is equal to 32.2 feet per second squared. So if you think about the units, if you take velocity, excuse me, 1 second. If you take the velocity at feet per second and you square that, the units will be feet squared per second squared. And if you divide feet squared per second squared divided by feet per second squared, the units come out to feet. And so now we've calculated the velocity pressure. And again, we can do a manual calculation, or we can do exactly what we did a moment ago using the same tables that we just used for velocity, 6-inch pipe, schedule 40. This time we're looking for the velocity head in feet. And again, 500 gallons per minute as the same exact value that we just calculated, 0.479 feet. Okay. Any questions about how we calculated velocity head and how we can look it up on a table? And again, you can use software when you're not doing manual calculations like we are today, or an app, or you can download a table like I just did from the internet.
Rich, here's the question. Do we have a maximum per head in feet?
In terms of velocity head?
Yeah.
So when you're designing a piping system, you generally look at the velocity, and if you're at 8 feet per second or less, let's go back. Let me click on that formula back here. Yep. Okay, let me go back. One slide. If you recall, we said our velocity was 5.55 feet per second, but in that previous slide, let's go back a couple of slides here at the design conditions, we said our maximum velocity was going to be 8 feet per second. All right, maximum flow velocity is 8 feet per second. So that means if we plug that value into this equation here, I have the velocity pressure. If I put in, instead of 5.55, if I put in 8 squared is 64. 64 divided by 64.4 is approximately 1. So if I'm limiting my velocity to 8 feet per second, by default, I'm limiting my velocity pressure to 1 foot. Hopefully that answers that question, Brett.
I'm sure it does. Would you define those tables you were showing as ASHRAE tables, or just general?
You can find them. I don't know if ASHRAE publishes them in that format. I looked on the internet for a nice table that was easy to read in a PowerPoint presentation, so that's why I selected that. And I checked the tables to make sure that they were correct.
10-4.
Okay, just continuing along here. So now let's look at the pressure drop through fittings, and we're going to use what is called the equivalent length method. Now, if you recall, we said the maximum pressure drop for our design conditions is going to be 4 feet per 100 feet. So that for every 100 feet of straight pipe, we do not want the pressure drop to exceed 4 feet per 100 feet. Now, if you'll notice, when we're looking at this chart tells us what the equivalent length would be for different types of fittings. So we had 6 inches a moment ago, so let's continue with that theme of 6 inches. So if we had, I'm just going to put my arrow next to the 6-inch column right here, 6 inches. If we had a standard elbow, the standard elbow, 90-degree elbow, would have the equivalent length of straight pipe equal to 16 feet. So if I am interested in finding out the equivalent length, well, all I'm saying is that if I had an elbow, in this case, a standard elbow, and I wanted to find out what the pressure drop would be. It's approximately equal to a length of pipe that's 16 feet long. And if you'll notice, for a medium radius elbow, the pressure drop is equivalent to 14 feet of straight pipe. And for a long radius elbow, the pressure drop is 11 feet of straight pipe. It's equivalent to 11 feet. So when I'm designing a system, I generally try to use as many long radius elbows as possible whenever I make an elbow in my design, because I want to minimize the pressure drop. Now, sometimes I'm forced to use a standard elbow because of space constraints, but if I can get away with it, I want to use a long radius elbow. And so this chart shows you for different fittings and a couple of different valve configurations what the equivalent pipe length is. And one of the ones I like to emphasize for comparison, we're going to do two. So this is called a gate valve. For those of you that are unfamiliar, that means that just as the name implies, it's like a guillotine type of gate that lowers into the water flow. And if I open the valve, the gate rises, and for all practical purposes, there's very little resistance. And if you'll notice, it's equivalent to approximately 3.5 feet of straight run of pipe. So a gate valve has less pressure drop than a long radius elbow. Going to the opposite extreme, a globe valve, which very rarely use globe valves in hydronic piping systems. We might use them for drain valves or something like that. Look at this. It has a length, equivalent length of 160 feet. So a globe valve has a huge pressure drop. It's the equivalent of 160 feet of straight pipe. Okay, so that's the basic concept that we are going to use for our manual calculation. We're going to use the equivalent length method. And we're going to say whenever we use a fitting, we're going to come back to this chart and use the value that's in here for equivalent length. All right, moving right along. Let's erase these little lines here and go to the next slide. What is a valve CV? CV is known as the valve coefficient, and by definition, it's the flow in gallons per minute at a 1 pound per square inch pressure drop at 100% open. Okay, so let me give you an example. A valve with a CV of 25 will have a pressure drop of 1 pound per square inch at 25 gallons per minute. So by definition, if you have, and most control valves are published by manufacturers with their CV associated with their valve. So if you see a valve and it's published, the data is published by the valve manufacturer, and it says that that valve has a CV, I'm making up a number again, say 35, then it will flow 35 gallons per minute and the pressure drop will be 1 pound per square inch. Very simple, very straightforward, but it's a common term that's used all the time, and that's exactly what it means. Okay, for US units, the units are gallons per minute at 1 pound per square inch, and if it's metric units, it's called a kV instead of CV, and the units are cubic meters per hour at 1 bar. All right, so if we're looking at the conversion factor, if I have data published for a valve that's in kV, I multiply the kV by 1.17 to find its CV. If I'm working in the metric system and it's provided in US units, then I take the US units, the CV, multiplied by 0.86 to find the kV value. So this little conversion here helps you understand the relationship between the US units and the metric units. Okay. Here is a chart from one of Taco's valve products. And if you'll notice on the left-hand side, it shows the valve size. So we're going to just pick an arbitrary size here. I'm going to say for a 3/4 inch valve, this is for the two-way valve right here, two-way valve. The first value that we see is the CV. So this valve will have 10.3 gallons per minute at a 1 pound pressure drop. And there's that other value of 8.9. So if I go back, let me go back, erase this for a moment and go back to one previous slide here. What was the conversion from CV to kV is times 0.86. So if I go over here and I multiply 10.3 times 0.86, that's approximately 8.9, and that's what it's shown here. So the calculation shows the relationship between the two. And the last value on this little chart, which is also helpful, especially if we're using the equivalent length method, is the feet right there, equivalent length of feet. So in other words, this 3/4 inch valve has a CV of 10.3. If we multiply 10.3 times 0.86, it'll come out to 8.9. That's the kV value, and it has an equivalent length of 8.4 feet. Any questions about anything we have so far, Brett? We're covering
Yeah,
a lot of.
let's bring a couple up here. One is, well, anyways, I'll read exactly what it says. How can I determine if an elbow is standard, medium, or long radius?
Excellent question. If you go into manufacturer's data for different elbows or fittings, you'll see that they will tell you what the radius is for the elbow for different sizes and whether it's a standard, medium, or long. Yeah, I always get the long radius. That's what I meant. They'll tell you on their chart. So you can just Google pipe fittings and you'll find a manufacturer, and then you could look at their charts and you can see the different sizes in terms of the radius of the elbow for different pipe sizes. So it's pretty straightforward.
Makes sense. Makes sense. And then the other question is, does fitting equivalent length correspond with a certain velocity? Does the
No,
value change with increased design velocity?
no, it doesn't.
Okay.
It's a fixed value. And because when we talk about equivalent length, then when we're talking about velocity, we get different values for velocity. If I recall, I think we just did we said in our case, we want a maximum of 4 feet per 100 feet. If you look on some charts, which we will in a minute, you'll see that the pressure drop for different flows will give you different values of feet per 100 feet.
Excellent.
Actually, let's take a second. I'm going to erase this here and go back a couple of slides to this slide here. If you'll notice, in our case, the pressure drop for the 6-inch pipe, there's my pen. Again, the 6-inch pipe, Schedule 40 steel. And remember, for this example, the first example, we're using 500 gallons per minute. So the pressure drop is 1.66 feet per 100 feet. So it's less than the 4 feet per 100 feet that we want. And if you'll notice, for different pipe sizes, that happens to be a 6-inch. For 5-inch pipe size for that same velocity, the friction loss is now 4.16. So if we were selecting pipe for this 500 gallons per minute, we would not use 5-inch because it exceeds our 4 feet per 100 feet of pressure drop. Hopefully that answers that question.
I'm sure it does.
I gotta go over here and get my pen again. Okay, moving right along. We talked about CV. Okay, now we have a very, very simple piping diagram, and we want to calculate what the pressure drop is. We're going to do a manual calculation. So let's assume that someone else has done the design, they've laid out the piping, and they know that they need 61.5 gallons per minute. So I'm going to click on my pen here. So we have a flow of 61.5 gallons per minute, and we used our sizing criteria not to exceed 8 feet per second. And when we did that, we came out with a 2.5 inch diameter pipe. And we have a layout. And the layout not only shows all of the pipe, the equipment, the fittings, the elbows, control valve, but also the equipment, the boiler, in this case, the fan coil. And this little diagram conveniently shows us the length of every section of pipe. So we'll call that 20 feet right there. Okay, so now let's label the points on this diagram. And I'm just going to do the first couple of points manually. And I'm going to erase all those lines. Yes, okay. So you can see the connection for the boiler. Let's say that that is point number 1. I'm going to put a number 1 right next to that. Circle it just so you can see what I'm doing. Actually, I'm going to switch colors. Bear with me 1 second while I switch colors because it'd be a little bit easier for you guys to see the color. Come on, where are you? Choose color. Okay, I'm going to pick blue here. So this first point connection on the boiler is, we're going to call that point number 1. And the second point on here is at the inlet of the pump, point number 2. And then at the outlet of the pump, that's connection point number 3. And then the next one, I follow the pipe all the way down, and where it connects to the fan coil, I'm going to call that point number 4. Put that right there. Okay, you get the general idea. Now in my next slide, hopefully I didn't screw this up, and I should have those points called out. So let's go to the next slide and see if I did that correctly. So we have a maximum velocity of 8 feet per second, maximum pressure drop of 4 feet per 100 feet. And in our case, we have 61.5 gallons per minute. So if I go over here and I'm looking at approximately, right here, approximately 60 gallons per minute, you can see my pressure drop for 2-inch pipe is 6.9 feet and per 100 feet. So I can't use a 2-inch pipe, so I'm just going to cross that off. 2.5-inch pipe says I've got a pressure drop of 2.72 feet per 100 feet. So I meet the requirement of less than 4 feet per 100 feet. And my velocity is 4.02 feet per 100 feet. So the 2-inch pipe would have satisfied the velocity requirement, but it would not have satisfied the pressure drop requirement over here. So therefore, I'm picking a 2.5-inch pipe. So that's how I decided to make that 2.5-inch pipe. Okay, erase that, go on to the next slide. Back to our diagram, and this time let's add those points in there. And I did it successfully. So if you notice,
they look good, Rich. They look good. It came out correct.
They do look good. So from the boiler, I'm labeling that point number 1. At the inlet of the pump is point number 2. Now you can start numbering your points any way you want, any order you want, in any direction you want. What's important is that you account for everything between each point. All right, so I simply labeled the points, and I have a total of coming all the way back to the boiler, I have 10 points. All right, and I'm going to do a point-to-point calculation. All right, so I'm going to set up a table. Let's see if I can do this. I did this properly, yes. So for item number 1 on our table over here, so we've set up a pressure drop calculation worksheet. And for item number 1, from point 1 to point 2, if you recall, it was just pipe. Point 1 to point 2, we had 2.5-inch Schedule 40 steel pipe, and the length of that steel pipe is 2 feet. So that's the length of the pipe. From point 2 to point 3, if you'll notice, I had, I'm sorry, from point 3 to point 4, if you'll notice, I skipped over point 2 to point 3 because that was the pump. I'm just interested in the pipe and the fittings for right now. All right. And that's what I'm up here, right here. It says pipe and fittings. So I've skipped over the pump. I'm going to go back to the pump in a few minutes. So from point 3 to point 4, again, 2.5-inch Schedule 40 pipe, 20 feet long. You get the general idea here. So keep going down from point to point. I've done 3 to 4, 5 to 6. My equivalent length of pipe is 2 feet. 7 to 8 is 20 feet, and so on. And then 9 to 10 is 2 feet. All right. And if I add all of that up for a moment, well, I'm not going to add it yet. Let me get rid of my lines here so that we can see what I've done. So here are the different values for the length of pipe. Now, if I go back, and let's go back to our diagram one more time. Where's our cursor? There it is. Let's go back here to our diagram. And if you'll notice, I have, again, the point-to-point measurements. I'm going to count the elbows. All right. It's all uniform. It's all 2.5-inch pipe. I'm using standard elbows in this little representation here. So I'm going to count the elbows. So I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Looks like I got 14 elbows. But if you'll notice in my worksheet, I put in 20 elbows. And that's because whenever I'm doing a design, I always throw in a few extra elbows in there in order to accommodate for something unknown. Now, it depends on how conservative you are. So I counted 14 elbows in my design, but the actual installation will probably take more. So I'm using a quantity of 20. And then each elbow has an equivalent length of 6.5 feet, if you remember that from the previous table. So it's just simply 20 times 6.5. So my 90-degree standard elbows have an equivalent length of 130 feet. And if I add that to these values up here, well, when I add might be a little different the way you guys add. So I do the big numbers first. 2020 is 40, 42, 40. 446, so 46 and 130 is 176. So now I know what the equivalent length of pipe is, including the pipe itself and the elbows. And if you recall, the pressure drop in feet per 100 feet was 2.72. So I multiply 2.72 times 176, and I divide that by 100. And if I do it quickly in my calculator to make sure I didn't make an error, 2.72 times 176. Remember, this is feet per 100 feet. Divided by 100, my pressure drop is approximately 4.8, so I rounded it off to 5. So there it is. There's the pressure drop for all my pipe and fittings, and there's the little chart that I set up for that. Any questions about how I calculated the pressure drop for pipe and fittings?
There's in general, there's a question here. That chart, where does it say in the piping pressure drop table that the values are for every 100 feet? Was that listed right at the top?
That's an excellent question. It's actually, I had downloaded just the page that I was interested in. The very first page defined all of different values. So I know from experience, and I know from reading the first page, that the values were given in feet per 100 feet. So that's a great observation on your part. It's not actually shown on the page that I copied and pasted for this presentation, but those are the values that are out there.
You had a semi-safety factor with your elbow count. You have a recommendation so it doesn't affect? This is an arbitrary question. You know, what is a typical safety factor for adding more elbows so it won't affect your pump selection too bad?
Well, you know, again, it's a kind of you're using a judgment call. When you do a one-line diagram and you're figuring out what the pressure drop is based on that one-line diagram, that one-line diagram has to reflect the pipe lengths that are in your actual floor plans themselves. And we know from experience that when you go from the one-line diagram to the floor plan to the actual physical construction, there's always going to be a difference between those three. When it comes to actual physical construction, we used to say, well, you know, the guy who wins is the one who gets first. The first contractor in is the guy that wins, because let's say, for example, The first guy in is the sheet metal guy. He puts all the ductwork in. Then guess what? If the second guy in is the piping contractor, he has to work around the existing ductwork. He's not going to take ductwork out and run pipe. So if the piping guy was in first, he'd get to run all his pipes, minimum lengths, minimum number of elbows, and then the sheet metal guy would have to work around the piping. Sometimes it's not that easy. You might have to move a pipe. So you can see that it all depends on the complexity of the system and what you think is going to happen. So it is a judgment call. There's no absolutes to this. So you have to use your best judgment. If you think you've got the right number of fittings, your calculation is going to be pretty accurate.
And here's a question that comes up a lot whenever we talk about pressure loss calculations. When do you account for elevation changes? Is there a difference for closed and open systems?
That's an excellent question. So we are talking about a closed system. Our diagram is a closed system. So the only effect that elevation has is static pressure, and that will affect the rating of the equipment. So in other words, if the pipe vertical length was 75 feet, that equivalent static pressure would be around 32.5 pounds per square inch. And so we would have to make sure that our equipment, and obviously it's 75 feet and 32.5 pounds is not a lot of pressure for most equipment. Most equipment's rated around 125 to 150 pounds. If we had a much taller building, it would affect the rating. We'd have to check the rating of our piping, fittings, and equipment to make sure we didn't exceed the static pressure. But in a closed loop system, the static pressure has no effect on pressure drop because when you send water vertically up a pipe, it's offset by the water that's coming vertically down. And so the vertical distance has no effect on the pressure drop. That's for a closed system. If it's an open system, we not only have to take into consideration, let's assume it's a condenser water system and it has a cooling tower. The cooling tower happens to be on the roof of the building, just make it simple. And let's say the vertical distance inside the cooling tower between the top of the piping and the bottom of the piping is 20 feet. Then we'd have to not only calculate the pressure drop as a function of pipe and fittings and equipment, but also the elevation change inside the cooling tower. And if that was 20 feet, we'd have to add that to our system pressure drop to properly size the pump. Okay, moving right along as the expression goes. Let's now look at not just pipe and fittings, but let's look at, we already talked about the equivalent length and the pressure drop in the pipe. Let's look at the equipment and the control valves, So if you recall on our diagram, remember I skipped over some of the points. So from point 4 to point 5, we actually have a fan coil, and the fan coil equipment pressure drop is 10 feet. I have one fan coil in our simplified system, and so the equivalent length is not applicable. So here's the important thing. Where do I actually get the pressure drop for the fan coil? The only place that you can get pressure drop for equipment is from equipment manufacturers' published data. You cannot calculate that yourself. You cannot look it up in a generic table. It can only be provided by the manufacturer. So in this case, I went to the manufacturer's data. I looked for a fan coil of the appropriate size. I looked on the tables for 61.5 gallons per minute, and the published data was a 10-foot pressure drop. Does that make sense to everybody?
Does to me.
Okay. Now, between point 6 and 7 on our diagram, we had a control valve that had a CV of 50. Remember, the control valve at a CV of 50 means that it'll have a 1 pound pressure drop at 50 gallons per minute. But our flow through our control valve with the valve 100% open is, I believe, 61.5. So now we have to take the ratio of 61.5 divided by 50 and square that value. Oh, let's do it again. Let's say 61.5 divided by 50, that comes out to 1.23. And now I square that, that comes out to 1.51 times 1 pound, because now the pressure drop is 1.51 pounds. And I have to multiply that by 2.31 to convert it into feet. That comes out to 3.5 feet. And that's the value that I used inside this little chart here, 3.5 feet. Does anybody have any questions about how I calculated that?
Nothing's posted, sir.
Okay, so I'm rounding that off to 4 feet over here on the right. You can see how I did that. Okay, the air separator, same exact thing as before. I have to go to the manufacturer's data, and for this flow and this pipe size, the air separator has a pressure drop of 5 feet. The boiler, again, manufacturer's data, 11 feet. I simply add up all of those values. That comes out to 30 feet plus, if you recall, the 5 feet, which is 4.7, and I rounded up to 5, comes out to 34.7 feet. So I've accounted for all the piping, all the fittings, all the equipment, and the control valve, and I now have a manual calculation that indicates that my pressure drop at the design flow of 61.5 gallons per minute is 34.7 feet. So now let's look at our diagram one more time, I believe. There it is. Excuse me. So there's our diagram, and I did the calculation. Now I'm going to fill in the pressure drop at 61.5 gallons per minute, 34.7 feet. Total pressure drop, 34.7 feet. If I add a 15% safety factor, then my total pressure drop times 1.15 is going to be equal to 40 feet. So when I select the pump itself, I'm going to select the pump at 61.5 gallons per minute and a pressure drop of 40 feet. Now the safety factor, sometimes that can be an office standard, or it could be what your personal preference is. Again, in this example, excuse me one second. In this example, I'm using 15% as a safety factor. You might use 20%. You might have an office standard of 25%. Whatever is appropriate for your system design is what you would use for safety factor. I find that 15%, if I'm relatively accurate on the number of fittings, the length of pipe, and I'm careful about looking up the data from the equipment manufacturer, 15% safety factor is a reasonable number to use. Brett, any questions?
No, there was a couple about safety factor. I'm glad you went over that. I think that cleared up those questions.
Okay.
And then, oh wait, why is the T fitting to ET7 not included, and why? So let's see. So, okay, let's talk about the expansion tank first.
Yes.
So why wasn't that included? Okay.
Well, in this case, my pipe size is 2.5 inch. The main pipe is 2.5. There's no flow into the expansion tank, so the flow into the expansion tank is considered to be 0. So for all practical purposes, the flow just bypasses through the T. Some people will include a pressure drop for the T. In this case, it's negligible, so I included that in my 15% safety factor. If I had a T fitting where I had branch flow going off to another device, then I would take into consideration the pressure drop by an actual calculation as opposed to incorporating it into my safety factor.
Sounds good. And then she continued with the question, and why was 2 feet instead of 4 feet used between AS7 and B7? Not sure what detail
what that
that
means yet.
Yeah. Anyways,
Between
maybe that's the
the air separator. I'm sorry, air separator.
Yeah.
And
B7,
the
boiler.
boiler. And okay, repeat the question, and maybe I can answer it now that I understand.
She said, why was 2 feet used instead of 4 feet Why was 2 feet instead of 4 feet used between AS7 and B7?
Oh, that's an excellent observation. This diagram is actually physically generated by the software called HSS, and we're going to show you that in a minute. And it shows the length of pipe from fitting to fitting, in this case from, now let me grab my pen, from this connection here to this connection over here. It shows the total length, and it repeats the length in a couple of different places. So you have to be careful, because in some cases it's going to be shown as a separate number. In other cases, it's going to be a repeat number. So in my case, I decided to use the 2 feet as the continuous length. But you're correct. I could have used either 2 feet, assuming that the length of pipe from fitting to fitting was 2 feet, or I could have used 2 feet between here and here. But if you recall, I did not make this a point. I did not number this as a point. So I simply said that it was 2 feet from point to point, but I could have just as easily used 4 feet. So that's a great observation on your part. Thank you. Anything else, Brett?
Nope. You got them covered so far, my friend.
So far, so good. Okay.
Good questions today, though. Really good questions. I appreciate that.
Yeah, these are great. Okay, we're on the home stretch here.
Yep.
So I'm going to select the pump, as I said a moment ago, at 65 gallons per minute. If you'll notice, I increased the flow for the pump. The actual calculation came out to 61.5. I'm rounding that up to 65. Let me just highlight that with my pen. I'm rounding that up to 65 and 40 feet. And that's what I'm actually going to base my pump selection on. Okay. Go back here and erase these guys here. Okay, and my final diagram, I peeled away. The pressure drop for the calculation was 34.7. That's what the computer calculated. All right, so I did the calculation manually, and I allowed the HSS software to do the calculation automatically, and we came up with the same number. Hopefully that demonstrates that. Okay. Before we go on to our questions, I do want to show you the actual HSS software. If I can click on here. This is the little diagram that we put together. And if you'll notice, in my PowerPoint presentation, let's go back here to the equipment. I have the fan coil at 10 feet. And hopefully I'm not going to make a liar out of myself. If I look over here and I double click on the fan coil, you'll see that the pressure drop over here, and again, today's presentation is not to show you how to use the software, but to demonstrate that if I do it manually or I do it using software, I come up with the same values. So in this case, oh, look at that. I lied, Brett. The fan coil, yep. I put it in at, in my manual calculation, I put it in as 10 feet. But on the software here, it's 5 feet. So I must have changed one of the other values to compensate for that. Let's look at a section of pipe here. I think this pipe was 20 feet long. So if I double click on that pipe, you can see there's the length of 20 feet. Here's the pressure drop. The actual head loss is 2.6 feet per 100 feet. And I think the chart that I used was 2.7 per 100 feet, if I recall. And it calculated the actual pressure loss for the pipe to be 0.5 feet. And in this case, it added a safety factor of 50% for the fittings itself. So the software, if I did the software calculation carefully, the software emulates what I did manually, and I came up with the same pressure drop. So again, this is the HSS software. You can download the software free from our website. I'm going to show you how to download that right now. I'm going to click on, oh my golly. Hold on one second.
You've gone into incognito. I like it.
I've gone into incognito, Brett, which is never a good thing. I'm going to Taco's website. And I'm going to click on apps, and then the next drop-down menu, Takeo Design Suite Software. Click on that, and if you'll notice, the very first package that's shown in the upper left-hand corner is, I'll use my little pen here, is the HSS. We also call it HS2, Hydronic System Solution Software. And if I click on, I get rid of my, erase that, and I click on where it says more info, it'll take me to a page where I can download the software for free. Now, you do have to register. If you'll notice in the upper right-hand corner, it says, welcome, Richard Medeiros. That means I'm not only registered, but I've logged on. And you have to register in order to download the software. So I'm not going to download it because it's already on my desktop, but I'm just going to click on the download. And here's where you fill in all of your information and then click on download. It only takes about a minute to 2 minutes to download the software. So that's just a quick reference. So we're at the point now, which I think we're doing well for time here. We have about 5 minutes for questions.
We have
Any
a great
new question?
We have a very good question. I like this question here. And it really comes into meetings and whatnot. When would you use a different max flow besides 8 feet per second?
That's a great question. So we generally like to be less than 8 feet per second because that's a reasonable velocity for sizing pipe. Now, if I have, for example, let's assume I had a chilled water system, and my chilled water system had terminal devices, and I'm just going to make up something. Let's say it had 50 fan coils, and each fan coil had a two-way control valve, and I was using some type of pressure differential sensor to control my variable speed drive connected to my pump to accommodate different flows based on the number of valves that were open in the system. So under those circumstances, I might size the pipe for a higher velocity. Again, it depends on your design criteria that you establish in your office. And I might have a design criteria of 10 feet per second for variable flow systems. The logic behind that is that the peak load might force the velocity to be 10 feet per second based on my pipe selection. However, the overwhelming majority of the time, you're going to run at less than 100% flow. So if it happened to be 1,000 gallons per minute for the peak design, and it spends the majority of its life, probably 85 to 90% of the time of its life, at less than peak load. So if it's less than peak load, it's not going to be 1,000 gallons per minute. It might be 800 gallons per minute. And so the overwhelming majority of hours that that system operates will operate at less than 8 feet per second if I size the pipe for 10 feet per second. I know that's a verbal description, but hopefully does that make some sense to anyone that asked the question?
Yeah, I think so. I've seen people use less than 8 feet for smaller pipe or in different locations within a building as well. So, you know.
Well, that's why you always have to look at two quantities. You want to look at your maximum pressure drop in feet per 100 feet, because like you said, Brett, when you get into the smaller pipe size, you might, at a certain flow, accommodate less than 8 feet per second, but your pressure drop might be, say, 10 feet per 100 feet, in which case that would be too small a pipe.
Right.
Any other questions?
I agree. Well, there was one about, and the gentleman, Thomas, that asked that question said, yes, definitely helped about the 8 feet. Why the CV values ratio for the two different GPMs is squared?
Excellent question. So when it comes to flow in a pipe as a function of system resistance, and let's go back here. We're going to go back here a few slides till we get to our table. Is this the table? Yes. So here we have, sorry about that. Here for a 2.5 inch pipe. Let's see if I can grab this. Yeah, for a 2.5 inch pipe, our pressure drop for 60 gallons per minute is 2.72 feet per 100 feet. That's that value right there. And it turns out that the pressure drop is a function of the flow ratio squared. So let's say that I went from 60 gallons per minute up to 70 gallons per minute. There's that 70. So if I take the ratio of 70 divided by 60, that comes out to 1.17. If I square that, I now have a pressure drop that's 1.36 times the value at 60. So 1.36 times 2.72 is approximately 3.7. And in this case, it comes out close. In this case, it's 3.8. So my calculation is relatively close to that. So I'm using that phenomenon so that when I increase the flow, my pressure becomes a ratio of the flow squared times the initial pressure. So in our case, our CV had a CV value, our control valve rather had a CV value of 50. So I had 61.5 gallons per minute was the actual flow through the valve divided by 50 gallons per minute. That was 1.23. If I square that and multiply that by 1, it comes out to 1.5 pounds per square inch. And then I multiply that by 2.31, which came out to 3.5 feet. So that's where that part of the equation comes from.
Good stuff. Good stuff.
Good stuff, cheap, as they
We're
say.
all caught up on questions, my friend.
Really?
Yeah.
Well, look at that. And we're just at the time we want to be, which is 1 p.m. Let me just go down to my question slide. Oh, my thank you slide. So at this point, if there are no further questions, and I guess there are none, Brett?
I can answer one of them when I get to say goodbye.
Okay, so at this point, I want to thank everyone for sitting in on our manual pressure drop calculation. Hopefully you got enough information that shows you where all of that software ultimately gets its information from. Today, in today's world, we prefer to do our pressure drop calculations using software, but periodically, whenever I'm doing a design, I might take a small section of the design and I'll do the pressure drop calculation manually to check it against the computer just to make sure the computer is not giving me a goofy answer. So with that in mind, thank you so much for participating in today's webinar, and I'll turn it over to Brett. Be safe out there. Brett, take it away.
Rich, great job as usual. And folks on the webinar, thank you so much for your questions and really made it very useful for everybody. Keep in mind, we have 5 more of these the next 5 Wednesdays: fundamentals of centrifugal pumps, centrifugal pump selections, and NPSH. Always a hot topic, the NPSH. Proper expansion tank sizing. And then the software Rich showed you, we're going to show you hydronic design, HSS software. And then the self-sensing pump theory and applications. So that's a topic that's becoming more and more prevalent these days. One of the last questions I want to answer: how do we get a PDH for attending? Tomorrow, roughly 24 hours from now, you will get an email that has a link so you can download the PDH right there. And if you don't get it, there'll be an email. You can contact us and we'll make sure you get it. So keep that in mind. And everyone that's saying thank you, we appreciate it as well. So I guess that's about it. Stay safe out there. Brett Zerba from New England. I'm not actually in Cranston. I'm in New England, though, Massachusetts. Signing off. Take care, everybody, and hopefully we'll see you next week. Goodbye.